Greetings and welcome to this lecture. We are in module 6, lecture number 5, that is strong inversion part number 1. In this lecture, we will discuss about what will happen when the device will operate in strong inversion. We will see the condition for forward saturation and reverse saturation. These are the learning outcomes of this lecture, which helps you understand how to identify that my MOSFET is working in strong inversion, weak inversion or moderate inversion, and how to derive the equation when the MOSFET operates in strong inversion. Let us do a quick recap. In previous lecture, we said that we do have a MOSFET and this is good way to represent the drain current in terms of terminal voltages. We have the terminal voltages as source voltage, drain voltage, gate voltage and body voltage. So, this is Vg, this is Vb. What we said is that we can choose either body as a reference or the source as a reference. Accordingly, we need to decide in which region of operation my MOSFET is working. For example, if I consider that VDB is equals to VSB, meaning I am considering body as a reference. So, I am applying the voltage VDB as like this and the source to body voltage like this. If I connect like this, in this condition what will happen? Both the channel end is in strong inversion like this. So, there are plenty of charges available into the surface and it is in strong inversion. Now, what will happen if I increase VDB greater than to VSB? When you make this situation, then this end of the channel is get tapered and hence the inversion charge near the drain end will be reducing, because we have found that when you increase VDB or VSB in general, then the surface potential will increase like this and beyond a point it gets pinched off to a value psi s A. And we also identified these voltages as VW, this voltage as VU and this voltage as VQ. We said that this region is strong inversion, moderate inversion, weak inversion and depletion. We have also claimed that we will decide the minimum limit of weak inversion in MOSFET operation based on the leakage current. When the leakage current is considerably negligible with respect to the overall drain current of the MOSFET, then we can say that is the lower limit of the weak inversion. In this scale, we said that we do have two possibilities to represent the terminal voltages, either in terms of VGB considering body as a reference or VGS considering source as a reference. Accordingly, we do have terminal voltages like VMB, VM, right, and we said that VM is in general nothing but Vt for V flat band voltage plus phi naught plus gamma times phi naught plus VSB. You can see here that if I want to represent it with respect to VGS, then I need to subtract by VSB. Similarly, if I am representing with respect to VDS, it is nothing but VDB minus of VSB. This is very important equation what we are going to use in this lecture. Let us get started our analysis only considering the strong inversion. As I have already claimed in the previous lecture that we need to separate these analyses in three regions of operation, which is strong, moderate and weak inversion, to simplify our analysis. So, let us start our analysis only considering the strong inversion. Again, let me clear the strongly inverted channel, meaning the highly inverted channel should be in strong inversion, which means if my source is strongly inverted and drain is strongly inverted, I can say my MOSFET is working in strong inversion. If my source is in strong inversion and drain is either in weak or moderate, I can still say my operation of MOSFET is in strong inversion. So, heavily inverted channel in general for NMOS, when you increase VDB over VSB, is near to source. So, let us consider for the first case as VDB is equals to VSB, meaning both the end of the channel is strongly inverted. And at that moment we can simply define the surface potential at both ends. Here we generally denote the surface potential as psi S0, and near the drain we denote the surface potential as psi SL. We have seen the surface potential in the strong inversion can be given by these equations. Psi S0 is equals to phi naught plus VSB, and psi SL is equals to phi naught plus VDB, where phi naught is nothing but 2 phi f, which we have already discussed many a times that it's a bad choice. So we need to add some delta phi to provide a smooth transition between weak, moderate and strong inversion. Now after this analysis, let's increase the VDB. If you increase the VDB over VSB, then what will happen? Here near the drain end the inversion will be reduced, and hence the channel gets tapered like this. Considering you are increasing VDB in such a way that it is not exactly 0, it means the QI will not exactly be 0. It does have some channel left with which the carriers from the source end will flow. That condition is called non-saturation. So we'll define what is saturation and non-saturation region of operation. This is called the non-saturation, meaning you are increasing VDB over VSB, but with some small finite value, not beyond VDB where the pinch off occurs. So we know that when we are saying that MOSFET is operating in a strong inversion, then the dominant phenomena of the current is drift, and we have already derived the drift component, which we called it as IDS1, is nothing but W divided by L mu into COX dash into VGB minus V flat band voltage into psi SL minus psi S0 minus half of psi SL square minus psi S0 square minus 2 by 3 gamma psi SL to the power 3 by 2 minus psi S0 to the power 3 by 2. This equation of drain current is in terms of surface potential at drain side and source side respectively. However, here goal is, can I represent this drain current equation in terms of terminal voltages? Yes, I can simply replace the psi SL and psi S0 by phi naught plus VDB and phi naught plus VSB respectively, because we know that when we operate the device in strong inversion, then the surface potential was given by phi naught plus VDB at drain side and phi naught plus VSB at source side. So just replace this and simplify this equation IDS1, or in general we can say IDS, because the whole current is dominant by the drift component. So we can simply ignore the diffusion component because we are talking about the strong inversion. So IDS can be written as W by L mu into COX dash VGB minus V flat band voltage into psi SL phi naught plus VDB minus phi naught minus VSB minus half of psi SL square means phi naught plus VDB whole square minus phi naught plus VSB whole square minus 2 by 3 gamma in brackets phi naught plus VDB to the power 3 by 2 minus phi naught plus VSB to the power 3 by 2. Can we simplify this equation? Yes, we can simply rewrite as phi naught plus VDB whole square as phi naught square plus VDB square plus 2 times of phi naught into VDB. Similarly, this equation can be written as phi naught plus VSB whole square is equals to phi naught square plus VSB square plus 2 times of phi naught into VSB. When you put here, you will see that this phi naught and phi naught term will be cancelled out, and you will left with this equation, where one term will obviously come as minus of 2 times of phi naught into VDB minus of VSB, right, divided by 2, where this 2 and 2 get cancelled, and you can simply separate out VDB minus VSB as one parameter and keep phi naught inside this bracket, and hence you will left with ID is equals to W divided by L mu into C aux dash VGB minus V flat band voltage minus phi naught into VDB minus VSB minus half of VDB square here minus VSB square minus this term is same as it is 2 by 3 gamma into phi naught plus VDB whole to the power 3 by 2 minus phi naught plus VSB to the power 3 by 2. Now this current equation we are defining as a new word N. Here N stands for non-saturation. It means this is a drift current which is flowing in a non-saturation, meaning VDB is increased over VSB, but not that high value at which the inversion charge goes to 0 near the drain end. So this is a non-saturation current equation when the MOSFET operates in strong inversion. I can simply show this equation as W by L, which is aspect ratio of the device, right, with some function of G as a function of VGB and VDB minus some function of VGB and VSB. You can see here this is a function of VGB and VDB minus VSB. Similarly, this is VDB minus VSB, and here also there will be VDB minus VSB terms will come into picture. VDB minus VSB means what? There is a lateral field which is in this direction, VDB minus VSB, and there is a vertical field which is coming from VGB, which we have already discussed that VGB is responsible to cause inversion and VDB minus VSB will cause to flow of that carriers. So I can simply represent my current equation considering that W by L is an aspect ratio, so I am taking it out and I can represent in terms of this. The beauty of this equation is it shows the symmetricity of the device, meaning if here I replace by VSB and I replace by VDB, then drain and source end will be interchanged. So that is what we generally say, that MOSFET is a symmetric device. The source and the drain voltage, or the source and the drain terminal can be defined based on the applied voltages. Now let us see what will happen if I am going to represent. Now can I represent the same equation without using the previously defined equations based on surface potential or charge and derive the equation of the drain current directly using the difference between quasi Fermi level which is given by VCB. So let us consider you do have a MOSFET. This is X direction, this is Y direction, and you are applying the voltages VDB here, VSB here. At any point along the X, let us consider the surface potential is psi X. In this direction the surface potential is psi X. Now if I want to represent the current equation, I can simply write a drift current equation as mu into W into minus of Qi into d psi by dx, where this psi is a function of x. So if you are in strong inversion, you can simply replace this psi x as phi naught plus VCBx, where VCB is a reverse voltage which is actually appearing across this inversion charge and the P body, right. The limit of VCB is nothing but VCB at x is equals to 0 is nothing but VSB, and this VCB at channel length L is nothing but VDB. So I can simply replace this surface potential as mu into W into minus Qi dash dVCB, which is a function of x by dx, and I can integrate these equation in the limits. The limit for x is 0 to L, where L is channel length, and limit for VCB is VSB to VDB into W into mu into minus of Qi dash dVCB, and in the left hand side you will get IDS considering its constant along the channel, so 0 to L dx. When you solve this equation, ultimately you will get this equation where we know that Qi dash can be given by this and Qb dash can be given by this. So we need not to go to solve the surface potential profile. Instead, we can simply rewrite this equation in terms of inversion charge and the terminal voltages. That is an idea to get the current for non-saturation by only considering the terminal voltages and the inversion charge. Now, if you derive this equation, ultimately you will ended up with this equation, what we have derived so far based on our analysis of surface potential. So ultimately, if I am going to plot this graph, this will look like this, where VDB can be taken in x axis and IDS is plotted in y axis, where if you closely see, when VDB is smaller, then this function will be dominant and hence you will get a linear graph, but beyond a certain point it will be a parabola, a inverted parabola, because this term will dominate. So there will be an inverted parabola. So we need to see which region of operation is correct and which region of operation is not, whether the current will follow this curve or not, right. The good point to see here is we are considering the body as a reference. That is what VSB term is coming up. If I am going to represent with VDS, then this point will be 0, it will start from 0. That you need to take care of. The second thing is, this negative portion of the current shows that the model what we are deriving, it is still valid for some negative value of VDB, though we have already argued that VDB should be positive, because this junction should be reverse bias. You cannot make it forward bias, otherwise what will happen, there is a huge forward current flows. But if you apply a small reverse bias, a small negative voltage, then this will be forward bias. For that reason of operation also, my model what we are defining here will hold good, correct. This region of operation is actually defined as non-saturation region, and this region of operation will see whether my drain current will follow this trend or this trend. Let us go back and analyze the equation beyond a point where we say that the surface potential is VQ, right. As we said that beyond a point where we said that VDB increases VQ. We defined already this VQ and VW points, which we said that when you increase VDB, then the surface potential increases from strong inversion to moderate to weak. This point is defined as VQ, VW, and this point is VU, correct. So if we operate the MOSFET in the voltage range which is less than VQ, meaning my drain end is in strong inversion and the source end is also in strong inversion, and hence this current holds good. What will happen if VDB increases beyond VQ? Then near the channel, then near the drain, my channel get tapered, and hence I do have a very narrow region over which my carrier flows, correct. Strictly speaking, beyond VP, the current is going to be saturate because it is not having enough space the carriers to go through, right. This point can be calculated by some means as considering the slope of the current is 0. So in the previous graph you can see this point we are talking about, where the slope of this curve DIDSN over dVdB is equals to 0. So I can calculate what is the value of pinch off voltage. We will use this equation and we will differentiate DIDSN by dVdB is equals to W divided by L mu into COX dash into. If you differentiate the first term, you are left with VGB minus V flat band voltage minus phi naught with respect to VDB. So, it is 1 minus half into 2 times of VDB, correct. Next, minus 2 by 3 into gamma into 3 by 2 into phi naught plus VDB to the power of 1 by 2. Here this term get cancelled, and ultimately if you equate to 0, you will left with a quadratic equation of VGB minus V flat band voltage minus phi naught minus this 2 and 2 get cancelled, VDB minus gamma times of phi naught plus VDB to the power 1 by 2, correct. This term can be written as VGB minus V flat band voltage minus phi naught plus VDB minus gamma times phi naught plus VDB to the power 1 by 2 is equals to 0, because the left hand side is 0. So, you are actually solving a quadratic equation. Let us consider this as A. The overall equation will be A plus gamma times A to the power 1 by 2 minus VGS minus V flat band voltage is equals to 0. This can be solved as A to the power 1 by 2 is equals to minus gamma by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage. So, A will be minus gamma divided by 2 plus square root of gamma square by 4 plus VGB minus V flat band voltage whole square, and now A is nothing but what? Phi naught plus VDB is equals to this quantity. So, the value of VDB at which the saturation occur is defined as minus gamma by 2 plus of gamma square by 4 plus VGB minus V flat band voltage whole square minus phi naught. That is this. We have already defined this term in terms which in terms of VW, in terms of VQ, right, where we need to modify this phi naught. So, what is pinch off voltage? The pinch off voltage is the value of VDB at which my drain current is saturated, or the slope of IDSN with respect to VDB is 0. So, this point is VSB, correct. So, this where the slope is 0. So, I can define the value of the saturation current as IDS dash. Please remember these notations, but we are going to use in our subsequent lectures, where IDS is defined as the saturation current. It means the current beyond this point, and IDSN is the non-saturation current, which is the current below this point, and this is the point which we called at pinch off voltage in terms of VDB, correct. Next, we can define what will happen. Next, we can see what will happen beyond the value of pinch off voltage. So, if the channel reaches the pinch off value, meaning you increase the VDB in such a way that the region here will be very narrow and the channel looks like this, you can simply say the channel is pinched off. At this point, the inversion charge tends to 0, or you can say it will become 0. If the inversion charge will be 0, to maintain a current continuity, we know that IDS is equals to W into minus Qi dash into Vd, which is drift velocity. If Qi goes to 0, it means to maintain a constant current in that region, drift velocity goes to infinity. This is not possible. I mean, you cannot expect an infinite drift velocity of inversion charges or the electrons, right, and hence there is a finite inversion charge present here, which is not 0. That is what, if you remember, we have plotted the inversion charge and the pinch off voltage, where we said that it is linearly decreasing but asymptotically approaching to 0, and that point we defined as pinch off. So we cannot clearly say that inversion charge will be 0. That is the reason the model what we have derived so far is only applicable for IDSN and not IDS dash, right? So we need to reframe our model. What will happen when we go for saturation? So at this stage we can clearly define my drain current having two subsections. One you can define as a linear part or non-saturation part, and the another is the saturation part. So the current will not follow this curve because I cannot use that equation. That equation is only applicable for saturation. It is not applicable when the pinch off occur. So you need to reframe this modeling, and hence what will happen, this component of the current is IDS dash and this is IDSN. This axis is VDB, this is VSB, and this is IDS. Correct? Here there is also a provision of reverse saturation, what we have discussed in the previous lecture, that if the voltage at the source side will increase instead of drain side, then the region of operation is get inverted. It means if you increase VSB over VDB, then the inversion charge near the source will be lower and the near the drain it will be higher. Our operation of the MOSFET will be still in strong inversion, but the current now will be reversed, and the same thing will happen in the opposite direction, right? And that opposite direction pinch off voltage can be defined in a same way. So if we'll summarize our analysis of strong inversion model, I can simply say that the value of VSB and the VDB decides in which region of operation we are. If the value of VDB is less than pinch off voltage and the value of VSB is less than pinch off voltage, you are in non-saturation region, and hence here the IDSN equation holds good. However, if VDB increases beyond pinch off voltage, right, in previous analysis we defined as VW, correct? VW beyond which the weak inversion starts. So beyond pinch off voltage, what will happen? The drain current is getting saturated, and hence you cannot represent the current by IDSN, you need to represent by IDS dash. This is called forward saturation when VDB is increased over VSB, and when VSB is increased over VDB, this is called reverse saturation. So let me summarize this lecture. We have seen that we do have few different regions of operations like strong inversion, weak inversion, moderate inversion. In this lecture we have discussed the strong inversion of operation extensively, considering that VDB is increased over VSB but not that value such that pinch off occur. Below pinch off we have defined that the drift current is dominating, and hence IDS is given by IDSN. We derived that IDSN and we found that our current versus VDB voltage graph is given like this, where below pinch off my current is increasing with VDB. However, beyond pinch off, this equation what we derive for IDSN will not follow, and hence we need to rebrush our equation to find out the saturation part of the current equation. So we will stop here for today. Until then, take care.